Okay, Warren asked a question, if I could give him a hint. I was looking for that code right there that I used to generate it. It's on my other computer. But I remember it not being it was pretty dense, what I did. So ask me tomorrow and I'll tell you, but it was meant to be something that you could probably get pretty easily with Ridge. So your small numbers are probably zeros. So everything was generated almost orthogonally. I did throw some noise around stuff, so there's a little bit of stochasticity to it. But no interactions are in the first one. So you don't have to do any weird recoding or anything like that. The third one, realistically, I don't think anybody will figure it out. And so it would be fun to iterate back and forth, but you can generate cases where you've got interactions in your data. And just play around with it and see how well you do with all of these techniques, and it probably won't do all that well. I threw a lot more noise in there, and it's relatively small compared to P in that example. So in those cases, I don't think you'll do a great job realistically figuring it out. You seem surprised. Try it. There's no illusions here. You can always build a forward simulator and see how well you do. And so what I'm surprised about is when people walk in and they say they can get everything right, the type 1s and the type 2s. So when there's a beta in there, they get those right. And when something's not right in there, they get that right too. So both types of errors that they control, and they'll be like 95, 95. No way. So this is not very complicated what you're doing if that's true. And when I see those sort of things in logistic regression, my experience is even on relatively easy cases, doing better than 85% that's pretty good. What you can get right in a lot of model selection techniques are what the main effects are. And so remember, in all these other cases that we're doing in reality, it didn't come out of this like y is equal to x beta model. That's just something we're using to describe everything. And so we're picking up on major trends and seeing if they make sense and if we can interpret them. I think it's one of the most common problems to do model selection, but it's hard to know. You don't know the generating function for the model itself. And so all this stuff that we learn in inference class, you assume you know the model. And so if you know the model, everything's easy, but there's now this other error function on what the model is itself. Here's some good news. Bayesians know this. So I'll address a little bit more about this when we get into SSVS. But for what you're getting is every time you get a vector of zeros and ones and it's the same in your give sampler, you're getting a posterior frequency once everything converges of that model probability. And so you might have some models that just come up a lot and they all explain the data pretty well. Some of them just look completely not that great. And so I think it's probably a bad habit to think there's a best model out there. It's like, given what criterion. Here's what we always do when we go to forecast is we average over those models. And so I'll let a mixture of models explain the data. And that's called Bayesian model averaging. And what you do is you come up with those posterior model probabilities that you're getting out of the SSVS algorithm. And so then I have one model with that much weight on it, and I have the right betas in there. And then other models that I can average over. And you can usually forecast pretty well. If you'd like to interpret, I guess you can. It's the average of those coefficients, And so, again, I don't put too much stock these days in to whether or not people have gotten absolutely the correct model. And it kind of is a pet peeve of mine when people talk about optimality, where it's like, to be optimal, you would need to know how the models are being distributed in the first place. We don't know. And so in stats, I think what we're really doing is we're coming up with shapes that fit data, and then we can transform those and recognize those patterns, recognize those structures, and come up with some inferences. So for a Bayesian, we always come up with our inferences on a scale of 0 to 1. So we're building a measuring stick. And there's some optimality properties, and I guess if you want to be a professor of statistics, you understand all of those. But in the real world, it's all about a fiction anyway. And everything's just getting soaked up into the air term. And hopefully there's not any higher order interactions, like three-way interactions, because that stupefies us. So anyway, people that don't even want to think about any of that, they've been running off and just doing neural networks. I'm just going to predict, and I'm just going to bag my neural network or something like that. So cross-validate. So it's not that surprising. There's lots of good stuff that's not controversial in statistics, but we probably don't highlight some problems are just harder than others. And there really is no paradigm for saying what is right. Again, you don't know how I've generated the models. So it certainly wasn't random in this case. I picked one. So, but if you didn't know, if I were trying to generate stuff out of a sparse space and I gave you too much, or I gave you all the stuff that you needed exactly to come up with the answer, those are very different problems. And we never know which case we're in. Anyway, I wish I could do better than that. I've heard it gone so far. Huh. I've heard somebody go so far as to say, I just don't believe in inference. It's like, what do you mean you don't believe in inference? It's like, I don't believe in the truth. Oh, interesting. What do you do with that? So I still choose to believe, and that we can do a pretty good job and explain things to the best of our abilities. Okay, Warren, ask me tomorrow at lunch, and I'll look at my code, and I'll give you an answer. But it's fairly dense, not a zillion zeros in there. And then the other ones get more and more complicated. And they're supposed to inspire you to build 4 generators so you can check to see how well you do. So if you're way off on Model 3, what it is, I'm not going to ding you really hard on it. I'd like you to be able to get Model 1 and do pretty good on Model 2, but I thought I would throw something out and just see all of the wild different answers that I get. So, okay. At the end of your give sampler, let's say address this question of, we get these vectors of zeros and ones, but we want the betas. So you want to know what the betas are. You don't want to just know presence, absence. This is pretty easy. So if I know which betas are in there, I know which x's to build into everything. And so let's just say I've got x. The actual x values for model, whatever your favorite model is. So I'll call it model star. And maybe model star looks like it's got an intercept in there. Oh, by the way, one of these problems, I didn't put a column of ones in there, but when I generated everything, I did have a column of ones and I had the intercept. That might be a model 1 case. So if you don't put your intercepts in your model, expect to mess everything up. So even if you had something like this, so some data that looked like this, so there's just one x and one y, and that fit is pretty good, is what I'm trying to draw. There is a line that goes through it. If you looked at all these residuals and you plotted QQ plots and everything, it'd be like, yeah, right on, I've got the right model. But if you didn't put the intercept in and you did something like this, y is equal to, yi is equal to xi beta, and you tried to fit this model, you would shove the intercept through 0, and that's how you would do it. And so you would just mess it up entirely without the intercept. And so what you should always do is in your X matrix, have that first column of leading ones in there. And so I didn't give you a full column of ones, just to make sure you guys do the basic things you're supposed to do, account for an intercept, blah, 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 blah. I think in model 2 there's some multico linearity. So you want to check for that and rip it out. So if you have two things that are correlated with each other, and I don't know, I did do this. I definitely did this. I did a linear combination of two things to derive the third thing. So, but you'd be able to pick this up out of a multico linearity test. So again, I was having a little bit of fun, and I want you guys to have fun with it too. So, but always build in your intercepts, no matter what. Even if like the data was down here, somewhere kind of close, just do it anyway. So if all of a sudden you're like, I don't have enough data to estimate an intercept, you've got more problems than you're letting on to. So just throw your intercepts in the model. If you don't do that and you're doing something like, if you're looking at the mean squared formulations of everything, you might be making some real errors. That some of those assumptions require you to have an intercept. Because remember, the null model in your regression class is just the intercept model. So if you're comparing models without intercepts to intercept models, you might be making a huge mistake. Okay, so let's say this model looks something like this. 1, 1, 0, 0, 1. Okay, so there's only 3 covariates, and I'm imagining maybe I gave you 5 things to start with, so I've overloaded your data set with 2 extra columns of x's. And after everything, your SSVS figures out, and no funny business, that you like this model. Now there was this question of what are you checking at the end of the day. So before we even answer this question of what are the betas in every step, what you're doing is your Gibbs sampler is running as you're getting vectors of these. At every step at the end of your iteration, you've got a full vector of 1s and 0s. And that's a posterior sampling. So what I would do is I would look at the posterior frequency of when you're a 1 or a 0. So you're going to come up with a big file that's going to look like this. So let's just throw this one in. Started converging down to this. You know, but maybe there's a 1 here, there's a 1 here, there's a 0 that showed up once. I'll just fill it out like that. So you can imagine this is a long combination right here. And so what I'm looking at is I'm going to be looking at, and this is after burn-in. So you need to make sure this thing is burned in. So what I would be plotting for my trace plots are maybe the posterior frequency of 1s and 0s. And so at the very beginning, as you're burning in, you know, maybe on your first iteration, it's like, okay, my posterior frequency is 1, my first time step, and then it was still 1, and then it was 1/3, so it jumped down right here, and then it started climbing back up. So I'm going to imagine this was a lot of runs. And so maybe for this column, if I ended up expanding this and having a 10,000 draws like you might, I have a trace plot that looks like this right here. I don't really want to look at all of this averaging of the frequency. I probably want to say, okay, it stopped converging right here, chop the burn-in time, and then compute this posterior frequency. So this right here would say that the model probability with an intercept in the model, if this was representing your intercept, it would say it should be in there. So maybe in this case, 1, 2, 3, 4, 5, 6. So with probability 5, or 1, 2, 3, 6 over 7. So whatever that number is, that's my posterior probability that the intercept is in there. So I would be checking this. Boom. And probably what I might also be checking is just the likelihood functions as well. So posterior model probabilities, what they are, and then maybe the likelihood function, because it accounts for everything. So not just each variable. So anyway, this is the interpretation. When you average these whole things up, that's your posterior model probability of inclusion of that variable. So I don't like to just look at that. I like to also look at what are my likelihood functions. So if I have 3 models, you know, that maybe share some variables, and there's another one And then there's some other variable that maybe has posterior probability inclusion of like 0.2, and I'm like, these numbers. You know, I like numbers like 0.9. 0.2 might seem good to me, but what I would do is I would compare it to my model without that thing in there and look at its likelihood function and see how much it wiggles. And I might be able to compute a Bayes factor or something like that and say something more technical and say, this variable looks interesting and maybe it's a little bit important, but it doesn't seem to change the overall likelihood or the Bayes factor too much. So I like to check all that stuff. But at minimum, I'd say make sure your inclusion probabilities on each one of the variables are converging to something. So you would not want to stop your sampler if it was doing something like this. It's like, whoa, you know, that's not converged. Definitely not converged. So I saw a few homeworks that kind of looked like this from the past where it's like, that's not converged. Echo didn't see it, but I saw it. It's okay.
So are you saying like the trace plot you would look at is just that first column, or like
all of them?
Yeah. Okay.
I would do this for all, you know, so for each one of these I would look at all of them. And so, and it's a lot to look at. So I'd come up with some sort of, you know, matrix of plots and stare at them and see which ones are converging and where that looks right. Again, I would build this up on a small example before I took it to your x's where you have 50 x's. So, and make sure things are working in a case where you've got 3 or 4 things in there and you've generated 10 numbers and just given them all. And so check the frequency of these and then check the likelihood. Okay, how do you get your betas? At the end of each step, you're going to have these x's. So this is going to be a matrix that looks like this. So this is going to have my x11 down to x n1 right here. I've got an x 1,2 down to x n2, and then I've got this last one right here. So this would be x 1 5 down to x n5. So that would be my x right there. So at the end of my iteration, if I wanted to look at the actual betas, and if you were doing full-blown model averaging and stuff like that, you'd probably want to look at them and know what they mean and, you know, oh, that's interesting. And do all your interpretation that you would learn in a regression class. That if I hold everything else constant and I change this x by 1 unit, then I get a beta unit increase in the y. There's a big fiction there. So in that interpretation that I never really like, you know what it is? If everything else is held constant. There might be like, that might be an extrapolation, and it's like, there's no case where I see data where x was increased by 1 unit here and everything else stayed the same. I never saw that. So you gotta be careful. So everything is comparative and controlled for by what's in the model. Anyway, I have this x right here. And I would just build the posterior distribution on my betas out of this. So this right here, you've got your sigma squared. You probably, if you want to do a really great job on this assignment, if you're running out of time, you might do some sort of willy-nilly estimation of this and look at sums of squares and do the thing that they might teach you in regression class and have a plug-in estimator. But you probably want to build that into your Gibbs sampler and update sigma as well at every step. It's all part of everything. But I would just look at this and I would just collect those betas out of here. So the betas that I would get out of here would just correspond to these, and I'd know that these other two are zeros. So at the end of each loop, I could learn what those betas are and then plug the other ones in zeros if I wanted to. And so what is this thing? This just looks like this. So e to the minus 1/2 beta minus x transpose x, and this is on my model, inverse X transpose Y. This is for my model star right there. So that's my mean vector. This is going to be transposed. Then I'm going to have my covariance matrix right here. So this is just X transpose X model star model inverse, and there's a sigma squared. That's this thing. And then you've got this beta minus the exact same thing that we wrote. So it's this normal distribution. Probably shouldn't have written it all out this way. X transpose X X transpose Y. Let me just rewrite that and say you have a normal model at the end of the day with X transpose for whatever this matrix is, or these models, so you tell you which X's you're using. Y doesn't change. And X transpose X inverse for that particular model times sigma squared. That's what it is. So at the end of each step, you can just sample your non-zero betas out of its normal model. So there's a good question. It's like when you report your model parameters at the end of the day, do you still use your ridge regularizer? And you'll hear different answers on this. So do you still regularize with lasso? You rip all that stuff out and what do you report? I just grab the X's and just report the posterior inference, and then I say, here's my non-informative analysis on what the betas are. And so I don't keep the regularizer on there. You'll see people do both things. So I don't think that there's any necessary rule, but remember what the regularizer was for. It was to squish things out to determine what the zeros are. So once we have all that, we don't need to continue to regularize. That's my opinion. You will sometimes see people keep the ridge regularizer in there, and if you'd like to, you can. Because I've seen other people do it, I just don't have a good reason for doing it. Like, why would you do that? You used it to squish everything out of the model, to figure out what was important, and now that you have everything that's important, free up the analysis. Liberate it. So maybe. These priors are called shrinkage priors. So we're shrinking towards something. Like lasso, we're shrinking everything towards zero. And so you have this pull towards zero, and I'd prefer not to have it when I report what the actual effect sizes are. So if you want your betas at the end of the day, at the end of your loop, just take whatever this is, your vector of ones and zeros, get those X's, and draw from that normal. Piece of cake. Then just remember which betas they are, because you're going to get, for this, you're going to get a vector of 3, and you need to remember that that's the first, second, and fifth covariance. So you need a little snippet of code in there to organize everything for you. But it's already indicated to you which ones there are. What else? So we've got convergence, what to kind of monitor. And we've got how you get your betas. There's Warren's question that I don't remember the answer to, but I've answered the best I can remember. And I generated that data last year, so I have to remember how I did it. But Model 1, not too sparse. Model 2 has some interactions in there. Nothing, I didn't make everything an interaction. to really just mess with you. But if you just check the correlation between the x's, you'll figure out which thing to throw away. If you have something where two of your x columns add up, there's some mixture of those things, linear combination of them, that makes another x column, you might ask which one do you throw away? Which ones? You choose. So if it were a science problem, you might have some preference. So, but in terms of just a math problem, it doesn't matter. They're all explaining the same thing. So throw away one of them for sure. So again, build some forward simulators, do your best with it, and enjoy the discovery that model selection is a hard problem. And when people come around and they say, my thing works 99% of the time, you can just nod and like, okay, whatever. So they're a marketing major, they're not a statistician. So it is a hard problem. If everything's orthogonal, and that's what we learned in our first regression class, do Graham-Schmidt, orthogonalize everything, do all this exploratory analysis, and then at the end of the day, do model selection. I think that still applies. Cool. Any like things that are you're just dying to know about the future of Bayes? You've heard about something, you want to know what it is, we never covered it. I tried to throw a little bit of fanciness at you guys for the end. And so I don't think the strategy was to overwhelm you and go, oh my goodness, I'm still trying to figure out how to come up with a posterior predictive analysis. It was to show you what the pathway looks like. These are the next steps. And if you take an advanced Bayes class, you'll probably spend a lot more time on this. Process priors, stuff like that. So it's supposed to just show you there's new stuff. I'm very aware that some people walk in, they can do all the math, and then it comes down to coding up their Gibbs sampler, and they're just, I can't get anything to work. And if you're in that boat, keep working at it. Just keep doing it, because these are cool tools, and just remember how flexible they are. So, for modeling all kinds of weird stuff, you can build crazy hierarchical models, use process priors, and infer everything in a Bayesian way. You're getting joint estimates of everything, and I think that's cool. So there's lots of flexibility. I didn't want to make it too simple. Anyway, I'm impressed with myself. I went through this whole class without saying anything about the likelihood principle, right? So I'll consider that a success. Here's the thing, when it comes to model selection, the likelihood principle doesn't apply. So basically, there's a principle that says if you have two likelihoods that are proportional to each other, you should come up with the same inferences. So if you have good reasons for coming up with priors, maybe Jeffreys, then you'll get the same analysis. So the likelihoods are proportional, and I have this prior that's invariant to whatever scale I put everything on. So if you're following principles like that, we should all get the same inferences, so long as we agree on our methodology for coming up with a prior. So there is a big if in there. For model selection, you need likelihoods over likelihoods. That's difficult. That's what a Dirichlet process is doing for you in some sense, is it's a probability distribution over probability distributions. So that thing I was drawing you today, that it's like I was generating these x's from these different clusters that were emerging. Each one of those clusters or components, that's a probability distribution in itself, and it's placing probability distributions on probability distributions. So probabilities on probabilities. That's kind of cool. Anything you can think of, you can do as a Bayesian. So will it matter at the end of the day how you build your measuring stick? Of course it does. So you have to run all your diagnostics. So the reality is this is just the fun part of Bayes, all the stuff I've shown you. The reality is revising your model, looking at your diagnostics, seeing where everything is wrong, and going at it again, and recoding up your Gibbs sampler again, and blah, 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 blah. That's what Bayes really looks like, and that's what all statistics should look like. So it's a lot of engineering, I think.
What's the emphasis in the advanced phase class in the department, or does it depend on who's teaching?
It does, but you'll usually see things like Dirichlet processes would be one of their go-tos. And if In-Young's teaching it, she'll spend a lot of time doing that. That's one of her favorite tricks for random effect models. They're mixture models, but those components could be random effects. And if you're a Bayesian, a random effect model just looks like any old model. In some sense, it looks like another hierarchical model. So that's kind of one of her favorite tricks. So if you're doing something like survival analysis, you'll see these models appear in an advanced phase class. So survival analysis is all about longitudinal studies. And you might have individuals that enter into a study, so you could think about something that's clinical, and they don't make it to the end of the study. So maybe they perish, maybe they have an allergic reaction to something, they need to exit, maybe their grandmother needs their help and they need to just move. Also, you could have people coming in from the other direction where it's, they enter a study late. And so you don't want to treat that just like it's everything else. And you wouldn't want to throw those data points away, especially if people are leaving the study. If they're perishing, that might be the most important thing. So you wouldn't want to throw that away. So I don't know if you know what a survival function is. It basically tells you the expected amount of survival given how long you'll endure, given that you have been in the study for X number of units. And so those functions, a lot of times they make them parametric. And so in the Kaplan-Meier thing is probably the easiest thing to do. But if you wanted more flexibility to it, you might think of mixtures of functions, and you could place Dirichlet processes on that. So they're going to start to teach you how to do some of this other stuff. It should segue nicely off of a class like this. So Bayes factors, we know what they are now. We know, at least in spirit, how to compute them, but what if I gave you something that wasn't conjugate and you couldn't do the integration? So now you've got computational choices. So they might walk you through algorithms like reversible jump or something to handle these cases and show you all the different variants of how you can compute these Bayes factors. They might, depending on who you get, teach you about the impact of the prior. So I kind of spent a little bit of time, I at least worked it out on the chalkboard with the conjugate prior, but what I kind of said is that places too much mass on the null. So I like these non-conjugate, non-local priors. There's a whole class of these priors. There's fractional Bayes factors, there's intrinsic Bayes factors, there's these non-local Bayes factors. And so if you got somebody like Chris Frank teaching the class, he would probably tell you it matters. And let's go explore all of them and see how much it matters. Something like that. So I think it would probably extend, but you'd see a little bit more process stuff and probably more models outside of normality, I'd hope. But it depends. But Bayes pops up everywhere. So this was meant to be fairly comprehensive, but we can't cover everything. So it should just be more techniques. I do have some good news. I hope to be able to teach the MCMC class soon. So probably not this next year, but probably the year after. So I'm going to be liberated. So I get to go back to teaching 3 classes, which would be good. So because I miss teaching that and data analytics and stuff like that. So if you've already taken my 2 classes that I've been offering for the last couple of years, some more should show up in the future. So. And then in like an MCMC class, I'd take you through lots of different algorithms that deal with certain situations. I should also say like factor models would be really an important thing to study in an advanced Bayes class, different hierarchical models. And so when you have hierarchical models where you have 2 variances that play with each other, you've got to be careful. So I think it would just extend to more complex cases, but in a nutshell, you know what a Bayesian does now. You're up to 1994. Cool.
There were a couple other questions in the Slack. One was, are we allowed to use software packages for Lasso and BIC? Those were
Yes.
Jen.
Yes, no problem. And I would be surprised if anybody did lasso by hand. It's harder than you think. I misspoke. It's not partial least squares. It's least angle regression is kind of the fastest sort of approach to estimating it. But going through that would take a couple days, and then coding it up would be hard. So let me just write it on the board for those people that just scan. You can use software. For lasso in BIC, AIC, what I would like is you to write your own Gibbs sampler for SSVS. But if you're acquainted with CRAN, there are all kinds of packages that already implement all of this. And so I think it would be a good experience for you guys to go and check that out, but you don't have to. So, but yeah, you can use packages.
Then Stephen asked about interaction terms. Is there a specific way to look for interaction terms in SSVS, or should we add more columns to X matrix? But I think you already answered that, and just like look at the correlations and
look at the correlations, but also when there are interactions, you need to expand X a lot, and then look at correlations there. I didn't do anything that's collinear in the interaction. That would be crazy. If I don't think that happens. It might happen, but I don't know if that happens in reality. I could certainly simulate it, but it wasn't to make your life an absolute nightmare. So I think you expand the X matrix, and that's why this is so hard in general. Even if somebody gave you 20 X's and you're like, I'm used to high dimension stuff, that could possibly be very high dimensional depending on how many transformations you encode into your regression. And so if you're doing three-way interactions, it's already a ton of stuff. So, but if I gave you 20 things, 20 choose 2 is a pretty big number. So even the two, those interactions. But what I would probably do is I would check for collinearity first on the main effects and get rid of that stuff before I check for interactions. It's just a quicker way to filter through a lot of possibilities. Yeah, it can get crazy. That's why if you had three-way interactions nowadays with the size of data sets, there's almost no hope. So.
And the last question was, is from Alex Bros. You mentioned in class that we might want to normalize the data before fitting. Can you go over that again, and why we do it, and how to denormalize the betas if that is necessary?
I wouldn't explain it like I would explain the regression on the normalized scale. So unwrapping them and stuff like that, you could do it. And so blow out their variance and reshift everything. But it's not super trivial on how to do that. So when you subtract off everything, you're playing around with the intercept and redefining what it means. And so a lot of times you're redefining the intercept. So I would say you can certainly just leave it encoded as the thing that best explains the whys. So unnormalizing the betas, probably don't need to do it. You could certainly do it though. But all I mean for normalizing everything, and this will be sufficient for this exercise. I used on some of the X's slightly different variances, not on model 1. And so it could have been the case that I used some sigma over here, and then I used some other sigma when I was generating all this stuff over here. I had some regression model for those, and I have some other ones for here. Just to make sure everything's on the same scale and that you're comparing apples to apples. Again, what we're doing with regression is we're just coming up with this additive function. And we like this because it gives us the ability to kind of compare things in a systematic way to each other. Everything should be kind of on a similar scale. So I'm just adding everything together, and things like the units shouldn't matter. So this is all we're going to do. So you're going to be starting with a matrix that looks like this. x11 down to x1n. I'll just leave n1. I'll just leave this as is. If you have an intercept in here, you don't need to normalize that. So that wouldn't make any sense. You just leave your columns of ones in there. And all I'm going to do is I'm going to sum these up. So I'm going to take my sum of the x, I'll say k1. So this is just my index going down right here. Where I'm going to, k is going to go from 1 to n, and I'm going to divide by n. That's going to be my mean for the first thing right here. And I'm going to also compute an estimate of sigma. So I'll get an estimate of sigma right here. This is for the first column. I'll write it here. This might look like this. Sum of the xi's, k1 minus x dot 1 bar squared divided by n minus 1. So this is your unbiased estimator. You guys must know I always do that, but it's fun. So n's big enough, it doesn't matter. This is just a better estimate. That unbiased thing is psychology. You know, it sounds good, but my answer is closer to the truth on average. So what I would do with this is I would take this column right here. So I'm going to remake a new matrix. And I'm going to take all of these entries right here. And I'm going to take x11. And I'm going to subtract off the mean. And I'm going to divide by sigma. So I'll take the square root of this and divide by sigma dot 1 right there. So this is the z-score. So this is one way of normalizing data. It's not the only way of normalizing everything, but it's going to put everything on a common scale. So, and I'm going to do that all the way through. So just to be really clear, I'm going to take xn1, subtract off its mean, same thing. So I'm doing the same transformation to everything in here. Sigma dot 1. Let's throw my hat on there. And so these right here are going to be mean 0 and variance 1. And so you probably want to do that and put everything on a similar scale. So that's all I mean. And you don't need to think any further about it. So no matter how I normalize, I make things normalizable so that I'm comparing apples to apples. So in this case, we're thinking about deviations from the mean. You know, and is there a certain deviation from the mean that contributes to explaining the variance in the y's? So that's how I interpret all my betas. Like, you know, at the end of the day, I'd come up with some betas. What would it mean? It would mean a 1 unit increase in the standard deviation would conform, or it would have whatever that beta quantity is. So a 1 unit increase on the standard score would increase y by beta 1 units if there was a non-zero beta attached to that. And I would do the same thing for each one. So just to be really clear about this, I'd go to x2, the second column, I'd get its mean, I'd subtract everything from that mean, and I would compute its associated standard error. I'd divide by that. Always a good thing. So I did throw a few little scaling issues in there just to mess with you, but they're not that bad. I didn't do anything crazy.
Is doing this, that lets us use psi² = 1 in our SSVS?
Yeah, it would be, so if you did that, yeah, so, and you would need to normalize the y's
Okay.
also, but then you might be able to use sigma as 1. So there's better estimates. Most of the regression people are going to go, now you should look at MSE and fit that model and then use those residuals to estimate what sigma is. You could do that as well. Or you could just update it in the posterior. I know, you're like, I don't want to write one more gamma update in my posterior. It's not that bad. But yeah, if you standardized everything, maybe you could use sigma's one. Check your residuals just to make sure you've done everything reasonable at the end of the day. What else?
Zach asked if mixture models and DPs will be on the final.
I might ask something about a mixture model, but not a DP. So, write down the posterior inclusion or the posterior probability of being in this mode. It's not going to be crazy. So the final is going to be designed just to reinforce all the things you've learned and give you practice so you can go, oh yeah. So you spend a few hours on it, write it up nicely, send it over to me, and enjoy your break. So it's just going to kind of capstone everything, tie a bow on top, and you can remember stuff from the beginning of class. Again, not supposed to be crazy. We'll see how I do.
Is that going to have any like computational things on it, or is it going to be more?
More math. Yeah, I think I gave you a computational exercise. So yeah, so I don't want to give you something that it could take you anywhere between 20 minutes to do a problem and 20 hours to do a problem. And computational problems are like that. And you just get used to it, And people that decide to tap out and not do it, they work for the rest of you. do it. I don't know if it's true. It's probably not. There's plenty of MBAs running around there telling people what to do and they don't know how to do MCs. So anyway. Is that good? Awesome, you guys. Well, it's been fun. I'm going to turn that off.